In this video, we're going to look at strategy for testing series. In order to identify whether a series is convergent or divergent, when deciding which test to use, it is helpful to classify the series according to its form. So I would say that identifying which test to use is the most challenging part about this chapter. So I put all of the tests together in one document, so that's going to be nice for reference. So the first test I want to look at is p-series. We have a series in the form of 1 over n to the p. If p is greater than 1, the series is convergent. If p is less than or equal to 1, the series is divergent. So this one's nice because you can kind of identify it quickly. There could be a constant like 3 on top or a -5 on the bottom, but you can just bring those values to the front, and then it's of p-series form. Next, we have geometric series. Anything of the form ar to the n-1 or ar to the n. To identify your r, it's the number being raised to the variable exponent, or if your series is in expanded form, r is your common ratio, and again, it's the number that you're multiplying by to get to the next term each time. Once you've identified r, you take the absolute value of it. If it's less than 1, the series is convergent. If it's greater or equal to 1, the series is divergent. Next, we have the comparison test. So if you have a rational function, an algebraic function of n involving roots of polynomials, or a series with positive terms, consider using the comparison test. It says, suppose we have sigma a sub n and b sub n, and they're series with positive terms. If we have sigma b sub n is convergent, and then we have a sub n is less than or equal to b sub n for all n, then the a sub n series is also convergent. If b sub n is divergent, and a sub n is greater or equal to b sub n for all n, then the a sub n series is also divergent. So what we have here is if this series is convergent, then something smaller than it will also converge. Or in this case, if we have b sub n is divergent and it grows without bound, that means something greater or equal to it will also grow without bound and diverge. It says to choose b sub n, keep the highest powers of n in the numerator and denominator. Or in the previous lessons, I called it the dominant term in the numerator and denominator. If the series has negative terms, apply the comparison test to the absolute value of the series and test for absolute convergence. Here we have the limit comparison test. Again, if you have a rational function, an algebraic function of n involving roots of polynomials, or a series has positive terms. It says, suppose a sub n and b sub n are series with positive terms. If the limit is n goes to infinity of a sub n divided by b sub n equals c, where c is finite and positive, then either both series will converge or both will diverge. The alternating series test, you'll have something of this form where you have this -1 to the n-1, or you have -1 to the n in front of your b sub n. If the series satisfies these two conditions, first, that the terms are decreasing, and then second, the limit as n goes to infinity of b sub n equals 0, then by the alternating series test, the series is convergent. For the test for divergence, you're going to use it if you think that the limit as n goes to infinity of the given formula doesn't equal 0. So if when you calculate the limit, if it does not exist, or if the limit does not equal 0, then the series is divergent by the test for divergence. For the ratio test, if you have a series with factorials or products or anything of the form b to the n, you're going to use the ratio test. So you take the limit as n goes to infinity, the absolute value of a sub n plus 1 divided by a sub n. When you evaluate it, you get L. If L is less than 1, the series is absolutely convergent and therefore convergent. If you get L and L is greater than 1, or if you get infinity, then the series is divergent. And if you get 1, the ratio test is inconclusive. We have a note, it says that the ratio a sub n plus 1 divided by a sub n in absolute value goes to 1 as n goes to infinity for all p-series rational algebraic functions of n, thus the ratio test should not be used for such series. For the root test, it would be something of the form where you have a power of n. You take the limit as n goes to infinity of the nth root of the absolute value of the formula. You get L. If L is less than 1, then the series is absolutely convergent. If you get L and L is greater than 1 or equal to infinity, then the series is divergent. And if you get 1, the root test is inconclusive, so you'll use a different test. And for the integral test, if you look at your function and you think that the integral of that function is going to be easily evaluated, then you'll use the integral test. Also, to use this test, f must be continuous, positive, and decreasing on the interval from 1 to infinity. If that's the case, we set up the integral from 1 to infinity of the function. If the integral is convergent, then the original series is convergent. If the integral is divergent, then the original series is also divergent. And then we have a note, it says to use the test, n does not have to start at 1. So your series could start n equals 2 or n equals 3. If that's the case, then you could just set up your integral from 2 to infinity of the function. And then also, just to be clear, this integral doesn't equal the series. We just use this integral to identify whether or not the series is convergent or divergent. Okay, now we have a flowchart that kind of helps us determine which test to use. First, you check, is the limit of a sub n equal to 0? If no, then the series diverges. And that's by the test for divergence. If yes or maybe, you can check, does the series have this form, 1 over n to the p? If so, you use the p series, and then you have this here. If no, you can check to see if your series is in geometric form. If it is, then you're going to use the geometric series test. If not, then you can look for absolute convergence, and then you're going to check, does the series of absolute value of a sub n converge? If yes, the original series converges. But if not, you can apply one of the following tests: limit comparison, integral, ratio, or root test. And then finally, if it's of alternating series form, if it is, then you'll use your alternating series test. All right, guys, thanks so much for watching, and please subscribe to my YouTube channel.